You know that the Arctic sea ice loss gets lots of attention, especially in terms of its impacts also, maybe on increasing the meanders in the jet stream and thus creating more extreme weather at lower latitudes, including the monsoon region and so on. And it's become almost like a showpiece for how bad global warming is and how rapidly it's accelerating. We have the Arctic amplification, sea ice albedo feedback, and so on. But is there a slowdown in the sea ice loss? Why? Because there is always the natural variability in the background, and it's important because once something gets lots of attention, it becomes to get a little exaggerated maybe, or not being communicated as scientifically accurately as possible. So when you draw trend lines, you can always just go from the beginning to the end and draw a line, and the variabilities within the time series may get ignored for communicating the urgency, or even maybe not being careful enough, and so on, with any without any malintention, etc. So let's look at this paper, which is a nice little GRL article, geophysical. My computer is not allowing me to bring up. There we go. I have an old computer which is giving. Okay. That's it. This is the first page. That's why it made the horrendous noise. Anyway, minimal Arctic sea ice loss in the last 20 years, consistent with internal climate variability. Why do they say that? Because they look for forcings, anthropogenic forcings, greenhouse gases, biophysical forcing, deforestation, other potential feedbacks, to see if the pause or the slowdown in the ice loss sea ice loss can be explained by still the what we call forcing. Forcing is where you are altering the radiative balance at the top of the atmosphere due to greenhouse gas increases, sometimes due to solar energy coming in, changing, and also sometimes volcanoes and so on. What are they trying to do? Over the past 2 decades, Arctic sea ice loss has slowed down considerably, with no statistically significant decline in September sea ice area since 2005. September sea ice is very critical because that begins to refreeze into the winter months, so where you are in September matters a lot. This pause is robust across observational datasets, metrics, and seasons. Large ensemble CMIP5 and CMIP6 simulations, the coupled model intercomparison projects under IPCC, which are used to do the future climate projections, they reveal that such periods with minimal sea ice decline under increasing greenhouse gas emissions are not unusual. So you will have an overall trend, but sometimes the trend just slows down. Analysis of ensemble members that simulate analogs of the observed pause indicates that the current slowdown could plausibly persist another 5 to 10 years. That's a projection, of course, although the chances of a faster than average decline are increased in the near future. The modeling evidence suggests that internal variability has substantially offset anthropogenically forced sea ice loss in recent decades. Overall, this observed pause in Arctic sea ice in Arctic sea ice decline is consistent with simulated internal variability superimposed on long-term trend according to the bulk of the climate modeling evidence. So we have to rely on models. Models are not perfect, and yet they can help us with these low-frequency variabilities. They are not good at local scales, better with temperatures than with precipitation, and sea ice models are doing pretty well, etc. Let's read the plain language summary as well, since many of my audience is not expert in everything, so they pick and choose what they want to listen to. Over the last 20 years, the decline of Arctic sea ice has slowed down substantially. Climate models from CMIP5 and CMIP6 show that pause in sea ice loss across multiple decades can happen even as greenhouse gas emissions continue to rise. When we compare the current slowdown to similar pauses in model simulations, we see that it could plausibly continue for another 5 to 10 years, although the same slowdown makes a faster than average sea ice decline more likely in the coming years. In other words, if you look at past slowdowns in sea ice loss, there is a natural variability which suddenly slows down the loss rates, but typically you have a time scale at which that pause lasts. So looking at the current pause, they are saying it is likely to go on for 5 to 10 years. Most of the evidence from these climate models suggests that natural climate variations have played a large part in slowing the human-driven loss of ice. However, it's not entirely certain whether the changes in the human influence on climate, that's the forced response, have also contributed to this pause. So it's always possible that, greenhouse gas increases and global warming are not warming everywhere. There are regions that cool, specifically like the Eastern Pacific or the Greenland, Iceland, Norwegian Sea in the North Atlantic, and so on, because of dynamic reasons in the way the system responds to increased energy trapping. Overall, while it may sound surprising that Arctic sea ice loss has slowed down even as global temperatures hit record highs, the climate modeling suggests that we should expect periods like this to occur somewhat frequently. So it keeps decreasing, but it has hiccups or slowdowns in the middle. So we have to understand what that means overall as well. Okay. So there are some numbers on what the reports have been saying about the Arctic sea ice cover loss. As Arctic sea ice cover is strongly tied to global temperatures, there would be little explanation of a multi-decadal slowdown in Arctic sea ice loss, and yet, as we will show, such a slowdown has been occurring in the last 2 decades. So it's physics that we have likely missed by focusing a lot on the trends and not paying attention to these slowdowns in the middle, which are likely just natural variability. In this paper, we document the recent observed multi-decadal pause in Arctic sea ice loss and address the following questions. How pervasive and robust is this pause in the Arctic sea ice loss? Are comprehensive climate models able to capture this observed phenomena? And if so, how likely is it suggested to be? How long could this observed pause plausibly persist for? And of course, what the implications are in terms of meandering of the jet stream, impacts on the monsoon and the lower latitudes, and so on. What is the role of anthropogenic forcing versus internal climate variability in contributing to the slow rate of sea ice loss? So they don't answer this necessarily because it's hard to deconvolve or separate impact of anthropogenic forcing. You have to remember that if there is a natural decadal variability and there is a trend because of anthropogenic forcing, then anthropogenic forcing will not necessarily remove the decadal variability, but it may modulate the period of the oscillation. So it's very tricky to separate. Okay, so the first figure here is on observed September sea ice extent, looking at 20-year trends of September sea ice extent with varying end year from 1998 to 2024, in which the red shaded envelope. So we'll see the details in a minute, but I should point out that 1998 is not a random year. There have been reports of a regime shift in the climate, especially in the deep tropics, especially in the tropical Pacific, and maybe this is related to that. There have been other regime shifts before as well in the mid-1970s and so on. Okay, so here are various data sets showing September sea ice extent, millions of square kilometers from 1980 through 2022 or so. And you can see that there is a decline, and yet there are periods where if you draw just a line like this, it looks like a trend, but there is definitely a flattening here, maybe a little flattening there, and it's there in this data as well. Okay, so these two figures are showing a 20-year trend in millions of square kilometer per decade. So you can see that there was definitely a drop, and then that drop has slowed down. And this is from 2 data sets. This is looking at seasonal trends. So end of the year end year of the 20-year trend. So these are two products. So we are looking at two products, NSIDC sea ice index and the OSI SAF sea ice index. So basically both data sets confirm that there are periods of slowdowns in the sea ice loss despite the warming continuing, even though there's been a debate about slowdown in the warming itself from 1998 to about 2012 or so. And that debate went on for a while, and again it's attributed to something that happens in the deep tropical Pacific in terms of ocean heat uptake as you increase greenhouse gases and so on. Okay, the percentage of ensemble members for each ensemble that have 2005 to 2024 September sea ice extent trends more positive than the observed value. The uncertainty estimate is calculated by Monte Carlo simulation, etc. Basically, there are lots of models. Then you go and see which models are capturing the observed behavior. You don't always you assume that the models are doing this for the right reason or for the same reason as nature, which is not necessarily always true. They could be doing the right thing for the wrong reasons, or models may, do something different from nature, even though they are doing many things similar to nature. So it's all very tricky. So this is percentage of 2005 to 2024 trends above observed. So trends that are stronger than observed. So all simulations are about 18% above, and these are CMIP6 and then specific models and non-sensitive CMIP6. So they have taken the models and made various classifications based on their trend in the sea ice Arctic sea ice cover loss trend. Okay, percentage of, that's for the period of 2005 to 2024. Percentage of trends remaining above observed. So you can see this is the these are the various models that they have considered, and they are looking at various scenarios for the future. So if there is a slowdown and the models do not capture this slowdown, obviously when they make the sea ice disappear will depend on how fast they are melting and or not representing the slowdowns, right? If you have these frequent slowdowns in the melt or sea ice cover loss, then obviously it will not disappear for some time, as opposed to the models where they are just maintaining a constant loss of sea ice. Okay, that's what the ensembles and the means are showing. This is for the total loss, and this is for September sea ice anomaly, sea ice extent anomaly in millions of square kilometers. So you can see that the anomaly will not completely disappear, but the range is very large, and this is going into a year 2050, and the loss here, the trends continue in many models, but again, lots of distributions around it. And this one model here, which is the IPSL, so French model, basically remains very flat here from 2030 to 2034, and this is from 2024 2034, so decadal, and this is for out to 2050. B, the conditional probability across each ensemble for the trends longer than 20 years starting in year 2005 to continue to be above minus 0.29 million square kilometers per decade. Basically, they are trying to see how much longer this slowdown will last, as opposed to ensemble mean differences in September sea ice extent between ensemble members with and without sea ice loss pauses over 2005 to 2024 period, continued into 2025 to 2050 period. Various ways you can slice and dice the model outputs. There are lots of models that participate in these intercomparison projects, and not all of them do the same thing. So when you look at specific thing like sea ice cover loss in the Arctic, there are some that are capturing similar pause as in observations for the real period of 2005 to 2024. You can take those models and see how long the pause may last and what happens into the future by 2050. Very important measures, right? The ensemble mean trend in September sea ice extent for the period 2005 to 2024 for each model and scenario. I didn't mention the scenario here, but scenarios are also included. Anything beyond 2025, I'm reading this in September 2025, so anything into the future is from projections, and the projections are typically for business as usual, or the CMIP 5 models had representative concentration pathways which focused on emissions and additional radiative forcing. You would get like RCP 2.6, which is the one that will keep us below 2 degrees C by 2100, RCP 4.5 middle of the road, and RCP 8.5, which is business as usual. In CMIP 6, we move to the so-called shared socioeconomic pathways. So they are SSP 1-1.9, which is the benign one that will keep us below 1.5 degrees C by 2100 and so on. So there you are looking at, difficulties in adaptation, mitigation, and the choices we make in terms of using fossil fuels, regional rivalries, etc., etc. Okay, so just get a sense of what's happening. So we are again looking at 2005 to 2024 ensemble mean trend in million square kilometers per decade. You can see the ranges are huge, from minus 1.6 to minus 0.2 here, and this is ratio of 2005 to 2024 versus 1986 to 2005 ensemble mean trends for the various models. So it gives you a sense that if you want to project into the future, you have to understand how much is caused by natural variability and how much is caused by anthropogenic variability, because anthropogenic forcing into the future is going to depend on the scenarios, and the model's responses to the scenarios are different in terms of the pauses in the sea ice cover loss and so on. So, doing all this very carefully, they conclude basically that it's perhaps surprising that while global temperatures have risen rapidly, reaching record levels in the last few years, in fact, Arctic sea ice cover has still shown no statistically significant decline over the past 2 decades. Nonetheless, analyzing 2 observational data sets and thousands of simulations from CMIP 5 and CMIP 6 archives, we have established the following facts which address the 4 questions raised in the introduction. The pervasive slowdown of Arctic sea ice loss is robust across the choice of definitions, observational dataset, and season. This observed pause in sea ice loss is simulated relatively frequently, a nearly 20% chance in climate models, and is thus to be expected even under high emission scenarios. So ice loss is happening, but there are pauses in the middle, so we must understand the details of that and impacts on warming as well overall, right? So warming is continuing, but warming is not monotonous either. Okay, not monotonic either. Okay, if model simulations are accurate, the recent pause may plausibly continue for an additional 5 to 10 years. They do the probabilities based on model performance in the past. However, or model pauses in the past. However, this pause also heightens the risk of a more rapid decline in sea ice cover in the coming years. That means you are paused and then you accelerate again. Nearly all models analyzed suggest an important role for internal climate variability in slowing the anthropogenically forced sea ice loss. Here, going all the way to 2024 is important because 2023 has been a record warm year. 2024 continued to be warm. 25 has continued. But I have another podcast where we saw that such sudden warmings have happened in the model records as well, and observations, and it shows that then slowly the system relaxes back to the previous rates of warming with anthropogenic forcing continued. Going forward, how can we use what we have learned about the recent pause in the Arctic sea ice loss? First, if internal variability has played an important role, then the present slowdown could provide a source of future predictability of Arctic climate change in the same manner as the papers mentioned here. Some studies have characterized this period as a regime shift in Arctic sea ice cover, which may also help to narrow sea ice trend projections. Second, the pause period could be used as an out-of-sample test in future climate model evaluation, like the early and middle periods of the 20th century. Nevertheless, the result of our study is a reminder that one needs to be cautious about multi-decadal predictions of the climate system, especially in highly variable regions such as the Arctic. Standing in 2007 or 2012, after having experienced yet another year of record loss and listening to assessments that climate models are flawed in their ability to reproduce the rapid loss of Arctic ice, it would take a rather brave person to have predicted that a sustained slowdown in ice loss was around the corner, although, as we have shown and several studies have documented, the current pause is entirely consistent with the state-of-the-art climate model simulations. So we have to understand if the models are doing it for the same reason as nature, as I said, and why only some models are doing, what is so special about them, and are those models consistently doing pauses in historic periods as well. There are data limitations, but nonetheless many questions remain, but it still emphasizes the fact that models have problems, uncertainties, biases, but they are still very, very useful. Okay, let's leave it here.